Hey boys and girls, this is just a quick intro. We have a little situation here that's coming up. We've got an open house, and the open house is going to be right here at our factory, and it's going to be on November the 29th. It'll go from about noon to 4 p.m. Costs about $200, and you get a chance to see everything there is to do about the Lightning and the Mach-E. If you're interested in these two cars and you want to have an in-depth explanation on how they work and what's inside, why don't you come and visit us on November 29th. You can find the information at the bottom of the description below. Thanks, and now I'll let you go and have a look at the Lightning motor.
Ready?
I'm ready.
Welcome back to Monroe Live, everybody. I'm Corey, and we have Kevin today.
How you doing? We're
going to go through the Ford F-150 Lightning front and rear motor. And this is episodes that... Oh, These are episodes that our viewers are always very interested in, so let's dig right in. Kevin, what do we have right here? This is a stripped down portion of the driveline, so we can explain how the power is transmitted through this electric drive unit. So let's start with the rotor, the stator. Where's the rotor right here?
So unfortunately the rotor is missing. So essentially we have completely delaminated every aspect of the rotor and stator assembly, specifically the rotor for this for costing.
And here's one of the laminates. So the magnets fit in these small little spaces right here. And you can see there's 1, 2, 3, 4 in this configuration. This is similar in shape, size, and geometry to what we see for Tesla, but instead of 2 magnets that we see in the Model 3, Y, and S, there's 4. And there's 2 little keys right here, and they'll slide right over and key in on the center of the rotor, just like this. Now, imagine you're driving your large F-150 down the road. You essentially have a stack of roughly 500 to 700 of these laminates reacting to all the force that's input from the stator itself. So here's a laminate from the stator, and we're just trying to visualize how you can turn all these kilowatt hours into forward motion. So here's the stator laminate, here's the rotor laminate, and it's going to react the force onto the center section of the rotor. Now, Kevin and I are going to very carefully dismantle this to show you how the power is transmitted.
Yeah. And this one here is the front electronic drive module itself. So it's overall common with the rear, but the big difference between the front and rear is the differential. So the differential in the front electronic drive module is smaller in general, with the ring gear specifically and everything else, than the rear. And it is an open differential as well.
Yeah. And this shaft is actually the output shaft for, I believe, the right axle, the right drive axle, and the left is going to react from the other side of the differential. So we're going to actually pull the center section of the rotor out. So here it is. It's similar in size to other EVs that we've seen. And then there's splines that interface with the sun gear. The reason it's called a sun gear is because you have the planet gears that will react against it. And the sun gear, I'm going to pull this shaft out right here. This small sun gear reacts against these 3 surfaces of the planet gears. Now this is how you're going to get that gear ratio. So typically EV drivelines are roughly 7:1 to 10:1. We see them in the 9:1 ratio. our team at Monroe & Associates has carefully counted these teeth and would know, sorry, we don't know the exact ratio right now, but you have roughly a 3-to-1 ratio from here to here, and this sun gear is going to react on the planet gears, and it will spin these sun gears, and they will react against this ring gear, and the ring gear reacts against these. So this is how you get your gear ratio up. You have a very small sun reacting against larger planets, and then this ratio you're dropping back down to a smaller gear that reacts against this. Oh, we don't want to take that off. That reacts against this ring gear. The ring gear is pressed into the housing. Now, Eric, you want to go over here and Kevin can show you where the ring gear is pressed into the housing. So all that force is going to react against the ring gear, which is stationary in the drive unit.
And these particular like differentials, you can see here the cuts that complement each other. So we could probably, it might get locked if we put it in, but essentially we could drop the ring gear in, and then they have dowel pins that locate the ring gear and keep it from spinning within the overall housing itself. There's a few ways, that some OEMs execute this. This is a conservative manner to do it, and it keeps allows like physical interference between the aluminum housing and the ring gear itself, and it keeps shavings and some other aspects of some simpler strategies that we have seen where essentially there's like knurled interfaces and the ring gear is pressed in, so there's no separate dowels or anything like that, and no snap rings. Ford has chosen not to do this with their internal EDM assembly, but this helps ensure that essentially there is no shavings or anything like that in the overall EDM itself. So it is a little conservative, but it does ensure that there's less issues down the road and kind of helps them get to long life for the overall drive module. So.
And now moving on, so imagine this ring gear is fixed. So as Kevin just highlighted, it's fixed into the housing. So what the end result is, the carrier moves. So this carrier is going to hold these pieces inside of the differential. So you have 3 small planet gears, and what these do is they allow, when you're turning a corner, if you have your left and right wheel moving at different RPMs, they can move relative to each other. So this will react against that large shaft that we showed earlier, which will go out to one of the wheels, and then on the other side, which you can't see, it'll be a mirror image to this, will go out to the other wheel. Now, this is being the front unit, this is not a locking differential, so it's always open. Is that right, Kevin?
That's correct, yeah.
Yep. And the ring gear is a different size on the front. So we have a smaller ring gear on the front and a larger ring gear on the rear.
That's correct, yeah. And essentially the rotor and stator assemblies are common between these, but the differential size is smaller. I wouldn't be surprised if you see essentially these families of motors or these different differentials, or excuse me, these different EDMs used in various configurations where, while this is a front drive module on a Lightning or maybe a future Expedition or something like that, this very well could be a rear drive module on a Mach-E in the future, going away from like a supplier source drive module to an internally provided Ford one. So
as a quick summary of how the electricity is transferred through the vehicle, you have stored energy transmitted to the stator. The stator then reacts against the rotor, pushing the magnets in the rotor around. Here's the shaft of the rotor, then spins the sun spins the planets, reacting against these surfaces. These surfaces then in turn turn the planets are connected here, and they'll react against the ring gear, and the ring gear then will move the carrier, and the carrier moving is what then will react to the shafts and the CV axles to move the vehicle down the road. This is different than some of the offset EDMs, electric drive modules we see, which essentially don't have a planetary set like this. They just have offset gears to get that. This has some advantage over packaging. And Kevin, you want to talk about packaging of these units compared to the Lightning?
Sure. So like overall, as we kind of just discussed, the differential would come in on this side here. And when you look at this is an extremely narrow package. If we had the Rivian set up here, or even some of the Teslas, in like vehicle length or the X direction, you'd see that this package is nearly double in size. Granted, it is relatively wide as far as the vehicle's overall cross width, if you will. So that does present packaging challenges between vehicle rails and things of that nature. But overall, from a fore and aft perspective, it provides a very narrow package, and it's one of the biggest advantages of EVs in general for front impact and rear impact is a lot of free crush space, because you no longer have essentially a stack up of an internal combustion engine with a series of pistons, however, V8, V6, inline 4, inline 6, or anything like that. You end up with these very compact drive modules that provide a ton of free crush space for the overall vehicle itself.
Yeah, and the inverters are relatively well packaged. They're thinner than others that we've seen.
Sure.
And let's see if we can get this lined up. Are they common in front and rear, Kevin?
Yes,
I didn't
I'm pretty
check that
sure.
out.
Yeah. And obviously they're separate. Given that these are probably a supplier sourced unit, of course the dowels are going to stick on this. It's pretty well integrated, all things considering. It's coming.
This on the blooper reel.
Yeah. So, but here you have essentially the internal portion of where the stator and rotor are, and this is the housing for the EDM itself. There's not a separate closeout. They just have this casting here, and they build this offline. And the top of this is a stamped steel panel that's closed out and sealed. And then it comes into the overall assembly itself.
And we've seen some improvement in the inverters as larger OEMs iterate from one version to the next. And this is not intended to be an inverter video, but I can run through the basic layout of that. So you have your DC coming in right here. So you see 2 leads. But then the location of the input is not as ideal as I would like it. So they actually come in and they have this overmolded bus bar. The only purpose of this piece right here is transmitting the electricity over to connect here. So when you're making decisions from a packaging perspective, man, would it have been nice to have the connector right here. Instead, it's over here in a less than ideal location, causing the need for this extra part. But there's probably a lot of decisions that went into why it's here versus here.
Sure.
Then you have your capacitor bank right here, and then the cooling channel surrounding all of your MOSFETs. Now these are MOSFETs, is that correct?
They're IGBTs.
Are they IGBTs?
Yeah.
Okay. Yeah, I don't know who the supplier is on this. I know our inverter team digs into this down to the very last detail. But essentially you have DC coming in here, capacitor bank. This is where your switching happens to switch from DC to AC. You have 1, 2, 3 IGBTs per phase. So you have 1, 2, 3 phase. These leads right here, 1, 2, 3, will interface directly with the stator, and the stator's right here. If you roll this over, you can see 1, 2, 3. And using these 3 phases, that's how you induce the field to then move the rotor, which we talked about earlier. Then to monitor the position of the rotor is done right here. Now this is on the other end of the case, and I know we call this a resolver, right, Kevin?
Yeah.
Kevin, you want to talk about this a little bit?
Sure. So essentially this, they're set per EDM, so there's some tuning, that goes along with them, but essentially it helps find out essentially some of the signal that's coming through, and then allows essentially the vehicle to know where the position is for the overall rotor and stator assembly.
Now we talked a little bit about the fasteners that were used here. Now Sandy Munro is a huge champion of eliminating fasteners, but when you have to use fasteners, what is something we don't like seeing here?
So typically we don't like to see different types of fasteners. Now there's something to be said for having that, depending on how this is built up. So essentially when you're bringing this plate here, which is one of those we love, it's the Evil Cat monocle here. But you can see these are all a similar style of external Torx plus style fasteners. So this can be built at one particular part of the station, and that's why they're discrete and separate from the others. And then when the resolver is brought on, it is a different style fastener, so it doesn't get mixed up or anything like that. But when you look at the overall inverter, and I want to say this is a Denso unit, don't quote me on it, but you can see here that all the same plane, all the same fasteners throughout. And that's something that we see often on the, a lot of, we'll say like Pacific suppliers, even Pacific OEMs like to commonize their bolts throughout for major assemblies that are being done. So there's pluses and minuses to doing it that way. You can end up with paying a lot of money and weight, even with having a standard fastener across the board versus tailoring them. You'll see a lot of tailored fasteners on like German OEMs, but they are relatively close together, and it is in some ways odd that they probably couldn't be used essentially using the same fastener. So
we want to thank Anker for sponsoring Monroe Live. They provided us with their GaN Prime line of products. Now, what is GaN Prime? GaN is gallium nitride, and what does that mean? That means you get more power, more wattage in a smaller package. Our team makes sure that when we tear this product down, the 727 charging station, they're using high quality components intended to last for a long time. You can see the GaN chips right here. So you have 1, 2. GaN technology will soon be prevalent in inverters for power converting in electric vehicles, but it's not yet out there. So if you want to learn a little bit more about high-end technology, look at gallium nitride. So if you want a premium replacement for your charging needs, consider Anker. All right, let's change gears a little bit and talk about the thermal systems for these drive units. So here's a plate heat exchanger where you're going to interface the ethylene glycol to the gear oil of the unit. So you'll have both fluids flowing through here, ethylene glycol here, and then this interfaces with the unit to get that heat exchange with the fluid. Now the fluid in the gear oil is transferred throughout the drive units with this pump right here. Now, when we first grabbed this, we're like, oh, look, it has a lot of composite for the body and some aluminum on the cap. And we remarked that it was almost the exact opposite of what we found in the Tesla gear oil pump. And now this one is slightly heavier, Kevin, and you said you did a little bit of research on the cost. So
sure.
At Monroe, we do cost analysis on all of our components. It's one of the core tenements of what we do for a living. And you said that this one was slightly more expensive?
Yeah, so it's about 1/4 kilogram heavier in weight, and materials and other processes besides that, typically cost and weight are very, very closely correlated.
If you have a common level of complexity
Yep.
in machining requirements. So these are serving almost the same purpose in a very similar
Sure.
unit. So the biggest lever for cost is going to be the amount of material you use. Is that correct?
Yeah, provided that they serve a similar function. And there's some debate about that. But in general, this, we have this at roughly a $10 delta between the two, where the this pump here is a little bit more expensive. Now, they weren't done in a bottoms-up fashion perspective as far as costing, but
And there's some micro differences we can notice right away. So just the thickness of the flange, first of all. So they're only using a single material right here, and then you have this anti-crush dowel right there. It's slightly smaller than what's used on the Ford one. Then you look at the seals. You have a double O-ring right here, and then you have a double O-ring here, but then there's a third. So you're like, okay, maybe there's 3 versus 2, but then there's 2 of these used. One has fallen out,
Yeah.
but there's 2 of these used. So you end up having 4 seals. Then with the large amount of plastic right here for the body, maybe you can get some cost savings there, but then the center section looks to be aluminum versus this entire body right here is aluminum. We talked about the connector. So this is like an integrated connector with 3 pins right there, and it looks like Ford is using a standard 4-pin connector that they may have used in it's a commercial off-the-shelf component
Sure.
for their wiring. It's larger, more material. The pins are larger, more material. And you have some wasted space if you're only utilizing 3 of the pins, even though it is a 4-pin connector. So these tiny inefficiencies, when you add up this 100 or 1,000 times over, means it's 100 or 1,000 grams. But Ford, being a massive organization, may have cost synergies by reusing this connector
Yes. Yeah.
millions of times on their vehicles versus more of a ground up bespoke connector that may be developed here for Tesla.
No, absolutely. And that's something we run into time and time again with some of the larger OEM clients that we have is, you look and you'll see some inefficiencies, but they're literally buying it in the millions at times of how they're sourcing it, and it's going across an entire vehicle portfolio. So that's kind of the double-edged sword of cost at times. When you're buying in volume, whether it's materials or different things of that nature, that can drive you into a decision that may not be the most optimum. It depends on how you're looking at it, but for that and that company or whoever it is, they're oftentimes unwilling to change from that because changing to this would be a new tool, a new part, new validation, and there's a lot of other things coming with it. They understand this, they like using it, and realistically for them, the juice is not worth the squeeze at times. So.
Yeah. And then Kevin, you had something to add about these two pieces.
Yeah,
right?
so it's just kind of interesting. So here you obviously, the Tesla was a little bit lighter in some regards, a little less complex because this even has a screen built in, and then the screen for this, the actual EDMs are on the housing themselves in a kind of a more conventional fashion. But one thing that's kind of interesting here is with respect to, these are essentially oil guides for the rotor stator assembly. So on my left here is a Tesla unit. So you have a glass-filled, I would assume it's a glass-filled nylon here. You can kind of see the sheen. And then essentially two like EPDM rubber shields. So when you look at this, essentially these are three discrete components, and there's assembly that goes into essentially loading and seating this together. Now granted, from a performance perspective, these are not directly analogous with respect to how
this is more splash and drip.
Yep, splash and drip,
pressure,
and that's pressure driven. But it is kind of interesting that when you start making these architectural decisions, I would say when you look at where the Ford has gone as far as how they are cooling and lubricating their EDM, they couldn't get a simpler execution of this. So they're using a material with its shape, and you can kind of see a little bit like with the edges here. And this essentially presses in. While it doesn't have any separate seals on it per se, it will lock into place and it kind of helps guide. So it's very, very simple, and it's honestly, it's a good execution if you're not doing a pressurized system itself. It's just an interesting dichotomy between the two with the pump, and then you look here and then with the different strategies.
And Kevin, now we're going to talk about how the stators are installed to the housing. So this is what we see more from traditional OEMs, a bolt-in stator. So there are some advantages and disadvantages. Let's start with something that we perceive as an advantage. It allows for adjustability to get the stator and the rotor aligned perfectly. So there's a tiny little air gap between the outside of the rotor, which I'll grab this real quick.
Oops, sorry.
And getting this rotor perfectly centered relative to the stator is very important. You want this gap to be as small as possible, and there's a little bit of play here. But maintaining that gap and that concentricity is very, very important for performance. If you have an off-centered rotor, that's not going to be good at all because you'll have an imbalance in the amount of force that's applied based on where the rotor is around, where the rotor is with respect to the stator. And the way they achieve that is these bolts right here. Let me pop this out. There's a little bit of play here. So it's not, there's going to be manufacturing GD&T. So it's important that they have a process in the manufacturing process to install the rotor and the stator and get them aligned and secured down. This is not what we see from other OEMs that don't have these ear tabs, and they'll actually press the stator into a portion of the housing. I believe we saw that on the VW ID4 and on all Teslas, particularly the Model 3, the Model Y, and the Model S Plaid.
And Eric, if you come a little bit closer, you can see a little bit what kind of Corey is talking about with the offset and the witness marks. And they're not directly concentric with each other. It's interesting that this is the temperature sensor for the overall unit. A lot of executions will interwove this within the overall windings themselves. It's more expensive, to do it as such, but this is kind of easier in some regards. You can service, not that you need to service it, but there was an issue. It'd be easier to pin down in testing. So it's interesting that they've spent money to get a separate connection here.
And then one of our favorite things to talk about is your park pawl mechanism. So only on one of the units, the rear,
Correct. Yep.
there is a park pawl, and we'll show you where that interfaces. So this is that Sun gear that I showed you earlier in the video, and this is slightly different from the Sun gear of the front, where they have added splines right here that interface with the target locking ring. This has mass. It's very important that it is manufactured very precisely, because it has to interface with the park pawl engagement arm right here. And there's an array of pieces and parts that go with it. And Kevin, you want to talk a little bit about why Ford still has a park pawl mechanism when other EVs are relying only on EPB?
Sure. One of the big things is truck requirements. So in general, oftentimes customers far exceed the capabilities of their vehicles when they're towing or doing anything like that. And more than likely, when you kind of look through Ford is looking through their requirement sheet, there's a requirement that this vehicle needs to be able to sit at GVRW or above, a certain percentile safety factor that they have on a certain incline, whether uphill, downhill, or anything like that. And they may not feel comfortable using an EPB system, even though there's quite a bit of force, and given the overall diameter, there's actually a ton of advantages for EPB, but they just may not feel comfortable with respect to either some aspects of how that system functions in these more extreme use cases. But typically that's why we see this, and probably why in any of the future Ford EVs and any trucks that they decide to electrify, we'll probably continue to see them given these kind of trailer towing requirements.
This is not a low-cost decision. You're looking at anywhere from $30 to $50 worth of componentry, plus the added rotating mass that will spin for the life of the vehicle that may or may not exist on other lower duty cycle EVs that are cars or small SUVs that may have to park on a hill in San Francisco, but don't have to park on a hill in San Francisco towing a 15,000-pound trailer with 3,000 pounds of payload and passengers. And then hold, for maybe 2 weeks. Sure. So we like to point out, these pieces that have really been a topic of conversation at Monroe & Associates for pretty much the past 7 or 8 years, once we started seeing EVs without them.
Yes.
Yeah. And our last topic is the locking differential. So we showed the differential in the front, and now Kevin's going to walk through the locking differential.
So as we kind of discussed there, the biggest thing here, what kind of Corey was mentioning, is essentially, if you want to kind of see here, this is the overall unit itself, as it kind of falls apart in front of me here. But you can kind of see a little bit of the difference. I'll pull it out slightly. So this is an electronic locking diff. And then this gear here, you can see the interface that it has. So when you engage this, and typically you can do it moving, I think up to 25 miles per hour. Oftentimes they actually disengage that fast, except for some of their more high performance variants. But this essentially will come in and lock this portion of the carrier to this gear itself. So once this is locked, even though there are spider gears, very similar to the other, the forward or front diff, excuse me, once this locks here, it essentially locks all of these. If you wanted to get this type of performance, you could weld spider gears, which is often done on some, track-only cars or off-road only vehicles. But this will lock this side here and essentially locks the entire portion of the system. And then both of your rear wheels now are spinning concurrently together and no longer can spin independently of each other. And while this is not necessarily advertised as an off-road vehicle, what this has with a front open differential and a rear locking is comparable to an FX4 level off-road package. So that's now essentially an entry level off-road package, because they have the FX4, the Tremor, which is essentially a decontented Raptor, no Raptor suspension bits, but that has a Torsen front differential. So but that's really in a nutshell kind of how it works. It electronically actuates, engages this, and locks the entire rear.
So Kevin, what's your overall impression of these two drive units?
So in general, like I can see from the conversations that we've had internally here with other customers that there's clearly an effort towards like overall efficiency and ensuring that these components last. When we looked at essentially the Mach-E, Ford has brought these in-house. I believe they're built at Van Dyke, the new assembly plant that they have for these. And when you looked at the Mach-E front and rear EDMs, two different suppliers, the housings themselves are extremely shrink wrapped and very efficient with respect to their overall packaging space and how close. I'll just spin this for you. These units live within respect to the periphery of them bolting on each of these end caps. So I think Ford has done a pretty good job, and I'll spin this around over here. And you can see with how close they're probably pushing some of their requirements, because they come in and they clean up a little bit of the edges, just to ensure they have the clearance that they need. But there is some interesting aspects because there's some legacy, I would say like transmission or case design with respect to these EDMs. That would be the oil pickup that we kind of talked about that wasn't on the Tesla, and it's separate and discrete. And this has an oil pan. One of the cool things about this is if there were metal shavings, this kind of can collect here, and it picked up within this pan here on the magnet and could be serviced or cleaned later. Yeah. But it is interesting that from some of the materials that we're seeing here within this blocking plate here, this is the Evil Cat plate again. Kind of looks like a cat with a monocle, or the Upper Peninsula, if you're a big Michigan fan. It's interesting to see some of these components and their material choices themselves. So this could be probably stamp steel or polymer, which they do in a lot of their other transmissions. Cheaper from a material perspective, lower density, lighter weight, as we kind of saw with the pumps. And same thing with this, big and thick. But I think it's timing, how fast they got this into production.
Yeah, and I have two major takeaways here from my assessment of these drive units. The customer is put the customer is put first. And I think that's really important is you could prioritize the shareholder and profit margins by underserving your client on this first EV. But I think with Ford, it's really important that their trucks serve all the purposes that Ford truck owners expect. And what that means is you get really robust components with high-end features and protections like a magnet and the filter, and then the cooling capabilities that we see. So I see that the customer's first, but I also see opportunity for improvement. So I think we're at a great period in time in the automotive industry where it's like a new renaissance. So sure. At Monroe & Associates, we had supported companies, tier ones, tier twos, and OEMs develop internal combustion engines that were more efficient from, essentially 1990 all the way through about 2010. So seeing this switch to electrification has opened up Pandora's box for improvement. And we see how Ford is excelling in some areas here. Other OEMs are excelling in other areas, in other powertrain and inverter and battery areas. So I think that the future is really bright, and I'm really excited to be able to see this transition over the next, I think, 5 to 10 years. I don't think we're there yet, but I'm starting to like what I see, and I think it'll only get better.
Yeah, no, I would agree. It's very interesting. So.
All right, so thanks for tuning in, everybody. Hope you got some value out of this video with Kevin and myself. Lots more to come with Monroe Live. Stay tuned. Thanks. Bye.